team that is working on this, and there is a list of people working on the project at the end of the presentation. So it's not a two-man project, far from there, far from it. All right, so first I'll introduce what is HIP. I think most people would be comfortable. It's a heterogeneous computing interface for portability. It's an AMD programming model, GPU programming model. It's very similar to CUDA in that it's a copy-paste of CUDA, and you change the prefix and you get HIP. So you can automatically translate CUDA programs to HIP, process we call HIPify. HIP programs, they run natively on AMD GPUs. They use their ROCm plus the LLVM client toolchain to compile, and the ROCm runtime. They also run natively on CUDA, NVIDIA GPUs using CUDA plus NVCC, and some preprocessor magic. So AMD provides GPU accelerated math libraries, HIP-BLAS, HIP-FFT, HIP-SPARS, in order to complement the same things on the NVIDIA side. So the idea is they have wrappers around AMD and NVIDIA GPU compute libraries, and so HIP-BLAS would wrap around ROC-BLAS and cuBLAS. So by design, it's supposed to be a high-performance programming model on both AMD and NVIDIA GPUs. So why HIP on Aurora? Well, we have two exascale systems featuring AMD GPUs, Frontier and El Capitan. So HIP most probably is a very likely target for many exascale applications. The previous systems used NVIDIA GPUs, so CUDA is prevalent here. And here comes Argonne with its Intel GPUs. And what are we doing to bring HIP support on Aurora? So I'd like to do a small tribute to Art Finkel, who left Argonne during ECP, but it was its original brainchild with some others at Argonne, but he was a PI at the time. And the idea was to implement HIP on top of level 0, which is Intel native API on Aurora, or OpenCL, restructure HIP to accept several backend plugins, and create a test suite of code of interest to us, support applications, of course, and implement HIP math libraries on top of one MKR. And of course, we're interested in investigating CUDA support as well. So the team that worked on this was made of the national labs. So we had Argonne, Oak Ridge, and NERSC. We had Georgia Tech and the University of Tampere at first through their Parments spin-off. And nowadays, Paganelsi, which is a former Intel Syria employee that is working from Lithuania. And we have AMD and Intel who participated as well in the project. So how does a HIP compiler work? So you take so it's derived, of course, from the C++ CUDA programming model. The idea is that you have a single source language with kernels inside the language, plus the device management API, which we call the HIP API. So you have several source code, and you have a dual path compilation process where the source code are compiled for the HIP device intermediary representation and the HIP host intermediary representation on an x86 machine. The LLVM x86 backend will turn that into a binary plus HIP API calls, while the AMD backend will turn the HIP device intermediate representation into AMD intermediate representation. The linker will bundle this device code into what we call a fat binary, which would be embedded into the executable that the linker would create. And when you run your application, the executable will be calling the HIP library through the API. The compiler called IPCC is doing all of this work. So what did we modify in order to make HIP on top of level 0 and OpenCL? The idea is to target a new intermediary representation for GPUs which is called SPIRV. It's a Kronos standard that is also used by Vulkan. Some of you may be familiar with it. The idea is we slightly modified the LVM heap front-end that AMD contributed, created a few additional LVM passes, used the LVM SPIRV translator from Kronos to turn the LVM heap device IR into SPIRV IR. And more or less, what you get is a fat binary that embeds SPIRV. And we had, of course, to develop our own library implementation of the heap API based on top of level 0 or OpenCL. So this is the scope of our modification. And of course, the modification we needed to put into LLVM have been upstream. So the idea is that for heap application, you would run CUDA on an NVIDIA machine, heap HSA on an AMD one, and ChipStar, which is our heap implementation, on top of level 0. And the CUDA ID is more or less the same. There exists a project called Luda, who tries to transcompile PTX to AMD directly as well, which could be envisioned to be used for CUDA application on AMD if you didn't want to EPify them. All right, so let's talk a bit about the software we support. So we have, of course, our ChipStar project. You can find it on GitHub. We built it from open source components, so the heap common repository, the heap test that we leverage, the ROCm device lib, which transforms the heap kernels into OpenCL calls. We support LVM 16, 17, 18, and 19. And we use, for now, the SPIRV LLVM translator. I have to mention that several Kronos members are working on an SPIRV LLVM backend, which should supersede the LLVM translator at some point in time, meaning that this part would be upstream into LLVM. So as I told you, we leverage AMD unit tests, which is very good for portability. We released version 1.2 at the end of last year. And 1.2.1. We're working on 1.2.2 with several fixes that we obtained with working with new project that I will be detailing. So we focus on stability and performance improvement right now, and also enhancing CUDA support. It's currently supported by LCF through the Pioneer C company, and Intel is also helping us. So CUDA is experimentally supported, but more on that later. So what library can you use if you have a heap application that you want to port on Aurora? So all the libraries we work on are actively supported. They are built on top of OneMKL, thanks to OneAPI and C-code interoperability. So we unified the architecture to interface with C-code and OneMKL, so developing new libraries is rather straightforward. So we delivered to the ECP project HeapRTC, HeapBlast, and HeapSolver. We're adding functionality into HeapFFT and HeapCub, and we are working on HeapRand as well, because there is some requests for this one. What are the applications we are working with? So we are actively engaging with the application teams. So functional application where we are optimizing performance are CP2K. Several CP2K apps are supported. We are working on libseed. There are a few problematic patterns, but more on that later. Games is supported, and Colin just told me yesterday that games, a heap version of games will be made open source soon, which is great news. We're working on OpenMM as well, and we have an in-progress work on enabling the Open Fan Wing Insight project. So it's a GE Aerospace, Boeing, and a third company. um, on their simulation code. And we're working at other projects, so always reach out if you are interested in the HIP application you want to port to orally. So be aware that we have some limitations. Some are on the kernel side, of course, and those apply to SQL port as well. So mask group function, the three-way argument shuffles, for instance, that people can use in CUDA, are not supported due to hardware limitations. We're working on emulating the case that we can, but this is a work in progress. Also, early exit from thread is something that will cause issues because of hardware limitations. So we are trying to work on compiled passes to alleviate these simple cases. But in the general case, it's not a tractable problem. There is no perfect solution to this. So you need to be mindful about these things. If you use them in your kernels, you will need to craft special version of those kernels for ChipStar. And you can detect ChipStar at compile time through environment through defined in the compiler. Of course, we're not supporting all missing libraries, so we can add support for new libraries. And if one of our projects is required, so it's as on needed basis. But the good thing is that Intel 1MKL and other libraries map very closely to the CUDA equivalent. And during ECP, we worked with Intel so that there were not a lot of divergence between the existing mass library and the new functions added into 1MKL to improve the portability of the applications. And of course, if you encounter a bug, report those and we will address that. All right. So we did a lot of benchmarking for the project. In this case, we used the Hackbench benchmark set. It's very nice because it has several versions of the same benchmarks in different programming models, so we can compare. And the goal was to assess the functionality of ChipStar for HIP and CUDA, and look at the pass rate on this benchmark set, and also compare with SQL running on the same GPUs and see if there were any performance discrepancy. So the first work we did was comparing, of course, measuring the success on the HIP benchmarks. So we are not fully there yet, of course, but more or less of the 261 benchmarks present in the suite, we successfully compiled 230. And of these 230, almost 200 ran successfully. Not all of these have result verification, but of the 92 that do 85 passed validation. And we've analyzed the errors. So sometimes we are missing implementation, of course, of some features, but that are not a priority to us. There are also runtime errors, hangs when the kernels have early exit, for instance, is something that we can find incorrect answers if some runtime calls are badly implemented, or if same thing, the early exit can result into incorrect answers. And some of them, of course, are ChipStar's error. We will need to rerun them because I'm pretty sure nowadays we will get a higher pass rate for this. And we compared the results with SQL to check that we are meeting the same kind of performance as the preferred programming language on Aura programming model. So it's a SQL time divided by the HIP time. So if HIP is faster on the left and SQL is faster on the right. So we can see that aside from some outliers on the side, the performance are pretty on par with one another. And the shell is log-log, so you can compare the distance on the left and on the right to get an idea of the kind of degradation you are seeing. So we also are portable across architectures. So this is the first round of tests we had when we had Gen 9 GPUs in our GLSC platform. So this was done by Jenny Chen, one of our interns. And the original measurement were the white dots. And what is interesting here is that by investigating those outliers, we found that we could, of course, increase our performance on the heap side, but we also have the second runtime fine performance bugs that were addressed, and you can see that we corrected these discrepancies thanks to the work which was done on the benchmarks. So let's talk a bit about CUDA support with Geekbench as well. So Jenny returned for a second internship last year, and she worked on the CUDA benchmarks, enabling the benchmarks to run with ChipStar. So she managed to enable 180 CUDA benchmarks. And of those 180, when she started, 88% were already working. But after her work, we're up to 96% of them compiling. And then 89% of those 180 benchmarks are also running correctly. And of the 89 that have validation, 99% are giving accurate results. So if we take a look from a pie chart point of view, this is a kind of a result we get. 172 compiling, 160 running correctly. Seven of them non-running or timeouting, and 3% of runtime error. And only one benchmark failed to pass validation. So one application highlight. Let's take a look at games. So games is General Atomic and Molecular Electronic Structure System. So it's a quantum chemistry software package. It contains CUDA and heap in order to target summit and frontier. So we wanted to port it to ChipStar with, and Colin is as a point of contact for games at the lab. So we had over 20,000 lines of heap and CUDA kernel code, multiple blasts and heap solver routine in the artful method. And the kernel use shared memory with sync thread to ensure synchronization between global and shared memory before using it. So here are the timing comparison. Those are recently updated. The porting effort was relatively low because the build system is supposed to be compatible. So we can use the same CMake for heap on NVIDIA, AMD, and Intel hardware. We had a thread synchronization issue because of the early exit that I was talking previously. So we had to account for that. But the STF time we obtain is pretty encouraging. So on A100, it's 1.66 seconds. On one GCD of MI250, it's 4.71 seconds. And on PVC one tile, we have 2.8 seconds. So the code was originally designed for NVIDIA hardware and optimized for it. And the port for now have been relatively straightforward. So I'll explain a bit the difference in performance. but we are pretty happy with the comparison between the AMD MI250 and the Intel PVC performance we get here. And the difference on AMD is mainly due to the Eigensoll in heat blast being relatively slow, whereas the Intel one is pretty fast. So I have a few minutes to conclude. So we delivered ChipStar 1.0, 50 ECP milestones. This was a working heap implementation, supporting applications and libraries, competitive performance with SQL. We are keeping working on it, funded by ALCF directly. So ChipStar 1.1, it was mainly performance improvement. And ChipStar 1.2, we focused quite a bit on CUDA and improving performance and stability. It's deployed on our platform. You can leverage either level 0 OpenCL, so Aura, of course, with PVC. But on GLSE, you have PVC and our Gen 9 available. We use ChipStar. ChipStar is used in other projects. So recently, a project called HipScript decided to use ChipStar to compile a heap and CUDA application for WebAssembly and running heap and CUDA application in your browser. I don't know if I feel confident about that, but that's a pretty nice outcome. People are also retargeting ChipStar to use on RISC-V targets. And that's very relevant in the context of European HPC initiatives. And perspective, so the native CUDA support is still experimental, but it's pretty promising. We hope to support more application and collaborate with new teams. HIP is constantly evolving, and we are focusing on application requirements to implement new functionalities. So we haven't started graphs, for instance, because we haven't seen really any application making use of them. But if you come with an application making use of graphs, then we would implement the graph API in an efficient manner. Same for the libraries. It's application requirements driven. For our supported platform, we are pushing extensions to OpenCL and SPIRI to better support HIP and CUDA, especially fixing subgroup size, three-way argument shuffle or extensions we are trying to push. We are working with ARM to have ChipStar work on ARM. We've worked with Rustical, meaning that Rustical is working on ChipStar, meaning that in the upcoming Linux release with Mesa support, we will see universal Linux support for ChipStar. And of course, we're looking for additional funding through the software sustainability projects. But we are always interested in finding more way to engage developers into our project. And with this, I am done, and I can take a few questions.
Thanks, Brice. Very, very interesting. So there's one on our chat. There are very few HIP-only applications. Most are ports of CUDA. When do you think it is preferable to use HIP on Intel GPU directly instead of SYCL? It said earlier today, it was said that automatic conversion works quite well. Or is using CUDA via ChipStar a goal?
Yes, using CUDA via ChipStar is a goal. We are working on enabling more CUDA. And you're welcome to try if you have a CUDA application rather than converting it to HIP. It should offer the same functionality because more or less we are just, CUDA and HIP are similar, so it's going through the same function calls anyway, just renamed. The other aspect of it is, yes, some translators work pretty well, but if you translate your application, it means you have a new backend to maintain in your code. So if you're not going fully SYCL, then you will have to wonder, do I want to maintain to backend or do I work with an alternative solution to try to make my existing backend work. I think this is a trade-off people porting applications have to consider. And it's also is interesting to note that on Aurora, there is secret interoperability between Chipstar and SQL, meaning that if some part of the heap is not working for you, you can port only a subset of your application to SQL, and we will be able to share the queues and the events and the memory between Chipstar and SQL. So you could only port a small subset of your application that is not sufficiently or correctly supported by Chipstar. So we offer a kind of staggered path to portability on Aurora as well. I hope that answers the questions.
Yeah, I think so. That it brought up a question that I have though. If you're using Chipstar, do you think that you can really just have one code base that runs across CUDA and HIP and PVC,
a HIP program should run natively on CUDA platforms and on HIP platforms, and provided you recompile it for our HIP implementation, it should run on Aurora as well. I'm not promising you won't encounter bug at first. We're working with GE Aerospace on their project, and we are solving bugs, and you can see the activity on GitHub. We're not finding the bug out of nowhere. It's because we're working with applications that we discover bug. So there are bugs, and we will work on them to address them. So, but it should be still lower effort than porting the whole code and maintaining a second backend in most cases.
Right. Yeah. I mean, I think that's a huge advantage to have a single code base that runs across multiple architectures. So. Cool. All right. I think we're at the end of our time, and I asked the last question there. So thanks, Brice.
Thank you very much.
We appreciate you virtually joining us.
My pleasure.